Hello. Today we're going to study Chapter 2, Sets, Functions, Sequences, and Sums. First of all, we have sets. So the simple definition of a set is an ordered collection of objects. Notice that it's not talking about objects that are different. Okay, so according to this definition, a set may contain repeated elements. So I just said elements. So the contents of the set are the elements. We call them elements or members. So we say that a set contains elements. So when we have these elements, we need a notation to denote that these elements belong to a set. So we're going to use this little symbol here. It's kind of a capital E rounded and a little bit smaller. And that means that A is an element of S. And to say that X is not an element of S, then we cross the little symbol. And this notation is going to be very useful, so keep that in mind. So sometimes we're going to have to use ellipses. So when you have a natural sequence or a logical sequence that it makes sense that these elements follow, it's very typical that you just use the ellipses, like in the example we have here. Now, sometimes it's very hard to list all of the elements in a set. So what we end up using is called a builder notation, which is kind of a shortcut notation. So you need a little bit more symbols for this. So the symbol that you will use very often is this bar. So what that bar means and how you can read it is such that. Okay, so this is like you have a subject in this example. This is a subject, and then you have a predicate to that subject. So subject and predicate, and then you divide them using the bar symbol. So under what conditions do we say that two sets are equal? Remember, we said that according to the definition of a set, the sets don't have to have the same number of elements, right? Because some elements may be repeated in one set, right? So if you are comparing two sets and you want to know if they are equal, you don't need to see the number of elements. All you need to do is what elements are in those two sets. A very peculiar set is called the empty set. And red flag here. This is a very common mistake. The empty set is a set that contains no elements. Okay? Right. And to denote that set, you use this symbol or just empty braces, and that means it's a set but has no elements. It's kind of the skeleton of a set. And then we have the singleton set. It's a set that contains only one element. So take a look at this. This is a singleton set. It's a set that contains an empty set. So we are using the braces to denote that it's a set, and then inside this set we have one element. That element happens to be an empty set. We have some examples of sets here, and I will take this opportunity to introduce very useful and very common sets. First of all, we have the set of the natural numbers. We use capital N in boldface to denote the natural numbers. Note that 0 is not a natural number, okay? That's very important. Then we have the set of the integer numbers. We use the Z for that. And then we use Q for the set of rational numbers. So what does it mean that the number is rational? It means that that number can be represented by m and n. So it's m divided by n. And these two, m and n, are both integer numbers. Okay? This is an important definition. Just keep this in mind. Put a bookmark right here, and it will become handy in the next chapters. We have another sets here. So in general, you can also have elements that are sets themselves, and you can keep going and going as many levels as you want. So X, for example, could be another set that contains another set that has another set, and so on. So we have some examples here of equal sets, and as we said before, the definition of a set says implies that you can have repeated elements. So in this case, we have this element A is repeated in this set. But are these two sets equal? Yes, they are equal, because if you go back and you look at the definition of equal sets, it says that they are the same if and only if, this is a double implication, remember, if and only if they contain the same elements. Okay? It's saying nothing about the number of elements. It's the same elements. Or they contain no elements at all. So with the examples we have here, these two contain the same elements. These three sets contain no elements, so they are equal. Okay. And one thing to keep in mind for discrete mathematics, and I guess in every mathematics course, is definitions. You always should go back and revisit the definitions. In mathematics, there is no ambiguity. The definitions are clear. They have no room for interpretation. They so every time you are in doubt, just go on and look to the definition. Another peculiar set, besides the empty set, is the universal set. So the universal set is a set for which all the other sets are subsets. In other words, it's a set that contains everything. So if you have the universal set, and with the previous definition, so we are ready to talk about Venn diagrams. So with Venn diagrams, they can be very helpful to represent and visualize complex combinations of sets. When we do the exercises, we're going to use Venn diagrams, and you will see how useful they are. We have a theorem here. We'll prove this theorem during the synchronous session. It says that for every set S, and then we have two parts. Part one is the empty set is a subset of S. Okay, so we use that symbol to denote subset. And the second part is that every subset is a subset of itself. If we go back to the definition of a subset here, it says that A is a subset of B if and only if every element of A is an element of B. So keeping that definition in mind, it is true that every element in the empty set, there are no elements, is an element in S. Yes. And every element in set S is in S, of course. So if A is a subset of B, but A is not the same, A is not equal to B, then they are said to be A is a proper subset of B, and we use that symbol. For example, the set of the natural numbers, remember natural numbers 1, 2, 3, 4, and so on, is a proper subset of the integer numbers. -4, -3, -2, -1, 0, 1, 2, 3, and so on. So natural numbers, the set of natural numbers is not the same as the set of the integer numbers, okay? But every element in the natural numbers is an element in the integer numbers. We have another two examples here. And then we have a definition. So often during the course we'll talk about infinite and finite sets. So as simple as this definition sound, we have to go through them and make sure that we are under the same understanding of what a finite and infinite set mean. So finite means that the set has exactly n distinct elements, and n is a non-negative integer, okay? So n could be 0, 1, 2, or anything else, okay? It cannot be negative, it has to be 0, 1, 2, 3, or more. And then we say that the cardinality of S is denoted by that, S in between bars, and the cardinality is equal to that number n, which is, again, a non-negative integer. And of course, if there is no way of enumerating the elements of a set, then we say that the set is infinite. Here we have another definition, the definition of a power set. The power set is denoted with capital P, and then A is the set. So the power set is the set of all the possible subsets of A. Okay. During the synchronous session, we'll go through this exercise and this definition will become much more clear. One thing to keep in mind is that the empty set is a subset of every set. Remember the theorem we talked about before? So the empty set is a subset of S. S is any set. So when you are computing the power set of A, you have to know that the empty set is a subset of A, right? So you should count that as a subset of A. And then we have Cartesian products. Cartesian products are particularly important when you talk about dimensionality. When you make a graph and you have the x and the y axis, what you're actually doing, what you actually have there is a Cartesian product of all the elements on the x axis against all the elements on the y axis. And if you have a three-dimensional, then you have a Cartesian product of three sets, four-dimensional, five-dimensional, and so on. To denote the Cartesian product of two sets, we use the cross symbol. It's kind of an X, but it's smaller, and then it has both sets on the sides. So the Cartesian, and then you read it as the Cartesian product of A and B, and that is equal to a set, right? And here we're using the builder notation. Remember builder notation. So this set contains the elements A, B, right? Such that that bar reads such that element A is in set capital A and element B is in set capital B. Okay? And as I said, if you have, if we're talking about a three-dimensional space, and you have the Cartesian product of three different sets, so then you have as many dimensions as you need, and the definition follows in the same fashion as for two sets. Okay? If all the sets in the Cartesian product are the same, then you just write the name of the set and then to the power n. That means n is the dimensionality of the Cartesian product. So in the previous chapter, when we talk about the truth values of a statement, of a compound statement or a proposition, and then we had a predicate and a subject, then we said that this compound statement is true under certain for certain values of the subject. So the truth set is those elements for which the predicate becomes true. So here we have how we use the notation. So the truth set of P of X is denoted by X is an element of D such that, builder notation, remember, such that the predicate for X is true.